So on the notes here, we're going to start with graphing parabolas, and we're going to do all of the conic sections. And they're called conic sections because if you take a cone, like in the parabola, we take a cone and we slice it, it'll make a shape, okay? This is a picture of all of them, and we'll do all of these conic sections because there's different ways we can slice a cone. We can slice it at an angle where it goes through just one piece, and that's how we make a parabola. We can slice it where we're parallel to the base of the cone, and that would make a circle, like the top of an ice cream cone. If we slice it sideways, it makes an ovally shape that's called an ellipse. And if we slice it straight up and down, parallel to the base of the cone, it's going to hit twice, and it makes two things that look like parabolas, but they're called hyperbolas. So the first one, we're doing our parabolas, and you did parabolas before. They were functions where we had y equals a times the quantity x minus h squared plus k, and we knew they made u-shapes, and the u-shape pointed up unless a was negative. If a was negative, it got flipped over and the u pointed down. We know that the a out in front also stretched or shrank the parabola because that was a vertical stretcher. We know that whatever's inside the parentheses with the x is going to move us left or right. And we also knew the opposite, whenever we're in parentheses, we go the opposite of whatever right says. And then the k number on the end was added on the outside, so that moved us up or down. And it went the way it was supposed to go because it was outside of the parentheses. So when we look at conic sections in this chapter, we're going to look at all these slices of a cone. And this first one is our parabola, which we've already done, parabolic functions. But we have a couple of new definitions that we could write out for parabola. We have this one, which is how it's a slice of a cone. A parabola is the intersection of a cone and a plane parallel to the slant height of the cone. So if this is the slant height, when you cut it, you have to be parallel. And that way, it never comes out of the cone. Like you'll lop off an edge, but this part would keep going up forever. And that's why you get the arrows on both ends. So you're not slicing entirely through the cone on both sides. The other definition is that it's the set of all points in a plane that are equidistant from a specific point in a line. So if we have a line, we call that line the directrix. We won't graph the line when we're graphing them, but that's what it's called. The point that they're talking about, the point in the line, is right here, and that's called the focus. So the first point you usually plot when you plot a parabola is the vertex. And according to this definition, the distance from the focus to the vertex is going to be the same as the distance from the vertex to the directrix. And that holds for anywhere else on the curve. So like if I went to here, this distance is going to be the same as that distance. And that's what makes it a perfect parabola shape versus some other shape. Okay, if I went all the way out to here, that's going to be the same distance as if I went straight down to this line. Okay, so that's the definition of what makes a parabola. The other part we have in there is the axis of symmetry, and that's what goes down the middle. And that's just where we have symmetry. If we plot a point, we could go across the axis of symmetry and we'll plot the same point. So that's what makes it easier for us when we're graphing, where we sort of count on one side and then just mirror it on the other side. So now what we're going to do is, instead of just doing quadratic functions, where our parabolas only went up and down, they always pass the vertical line test. But now we're going to do conics that are considered quadratic relations. So they are not always going to pass the vertical line test. So let's go back to inverses. So when we did inverses, we reflected over the line y equals x. So if we took this parabola of y equals x squared and flipped it sideways, it would go like this. Now, when we write that, we can do it two ways. If you wrote it as a function, the top part was y equals the square root of x, and the bottom part was y equals negative the square root of x. But we don't want to write it as two separate functions. You can think of it just where if we started with our y equals x squared and we switch x and y, then it would become x equals y squared instead. And x equals y squared describes all of these things with one equation rather than have to write two separate equations. Okay. So now we got a second family of parabolas. In these parabolas, our basic format is going to start with the x equals instead. The stretcher or the number out in front, we're still going to call a. And if it's a negative, it's still going to flip us. But instead of flipping us up and down, it'll flip us left and right because it's affecting x. Then inside the parentheses, we're going to have y. The vertex of a parabola was always called HK. Don't ask me why they chose those letters, but they did. So K is the y value of the vertex. So we know that what's inside with the y should change the y value. So we're going to put a K in there. And this is going to be squared. And this K right here now is on the inside, so it's always going to have the opposite effect, just like it did when we took the opposite direction with x. Okay. And then the number on the end we're going to call h. And h is going to affect the x value of our vertex. H isn't inside parentheses, so it's going to go the way it's supposed to go. So a plus is going to move us to the right, and a minus is going to move us to the left. Okay, so this is from the worksheet on graphing parabolas, and there's an example on here. X equals 3 times the quantity y minus 3 squared, and then the plus 2. So this is the information that we're going to be able to give about a parabola. We're not necessarily going to give all of it ourselves because we're not going to use calculators when we do this unit. Everything's going to be no calculator. But we should be able to tell by looking at it. First off, it starts with an x, which tells us it's a left-right parabola. Since there isn't any negative, that tells us that we're going to open to the right, and our parabola is going to go like that. Okay. If there were negative, it would have opened to the left instead. The next thing we like to do is we want to put the first point on there, so we go to put on the vertex. The weird thing about this one is we have to remember that the number out here is the x value of the vertex, because that's technically belonging with the x. So that's going to move us 2 to the right. So we start out and we move over 2 to the right, and that's the first thing we do. The y value of the vertex comes from what's inside with the y, and we're going to go the opposite direction of what it says because it's inside parentheses. So we're going to move positive 3 or 3 up. So then we go onto our graph, and that point moves 3 up, and that's where our vertex is. So we're going to plot the point. Okay, so then we have to get the rest of the points on our graph. So our normal shape for a parabola, when we had x and then y equals x squared, was 0 squared was 0, 1 squared was 1, 2 squared was 4, 3 squared was 9, and we could keep going. But in this case, we've switched x and y. So really what's happening here is this is now the y, and this is now the x, which is the y squared. So all that means is when you're counting, instead of going over and up each time, you're going to go up and to the right. But you're going to follow the same patterns as when you were doing it. You're just sort of turning your paper sideways. So from here, we would normally go 1 squared is 1. But instead, I have a 3 out in front. So I'm tripling. So I'm going to go up 1 over 3. And that's how I get my next point. I mirror it across that axis of symmetry down the middle. So let's write that one down too. The axis of symmetry is a line. It's a horizontal line, so it would have to start with the y equals. And it's whatever the point is that went through the vertex. So our axis of symmetry over here was y equals 3. Be sure you write it as a y equals 3. And that's what tells us whether it's a vertical parabola or a horizontal parabola, based on which way the axis is going. So if you wanted to do any more points, they're not going to fit, but you would normally go 2, 4, but we've got to triple how far we go, normally up, in this case to the right. So we would be going 12 in this direction, and that's not going to fit on the paper. So this is all I really need. Are those 3 points are all that's going to fit on this. I do have to put the arrows on the end to show that it keeps going forever. We are not going to find the focus and the directrix but I just wanted to mention what they were and how they work. So if this is our directrix right here, and this is our focus, that means if I were to count this right here, that's exactly 3 units long. And if I counted this at an angle right here where it is, that would be exactly 3 units long as well. Okay, so that's what makes this shape. So one of the cool things about parabolas has to do with this focus directrix thing. It's called a focus because if you were to take a wave, like let's say this is a satellite dish. Satellite dishes are usually parabolic, like you see the DirecTV stuff, and they have, in the little dish, they have that little thing in the middle, right? And that's at the focus. So what happens, based on the shape, is any wave that comes into the parabola is going to bounce at an angle so that it's going to go through the focus. So like if I take a wave that comes to here, it's going to bounce and go through the focus. If I'm over here, it'll go through the focus. So when you have something like a satellite dish, or if you see on the sides of a football field, you know how they have that plastic thing with the microphone in the middle, or you see them in spy movies where they're pointing it around. It can take what would not be a loud enough sound or signal for you to hear, and because it puts all the beams through the focus, then it gets a strong enough signal to figure out what something is. So we still need to say the domain and range, just like we always did. In this case, for a regular function, the domain was all reals. In this case, it goes up and down forever. So the range is going to be all real numbers, or from negative infinity to infinity. And the domain, you just got to look from the vertex. We go from 2 to the right, so we go from 2 to infinity. You make sure that 2 gets a bracket, because you can equal it, and all your infinities, remember, would have to have parentheses, because you can't equal them.